Welcome to the 12th lecture. We are going to study chapter number 2 from this point, and we're going to start chapter number 2 from this point, that is about numerical measures. Before this, in chapter number 1, we have been studying charts or graphs for quantitative and qualitative data. We studied graphs for quantitative data like bar chart, pie chart, dot plot, stem and leaf plot, and frequency histogram and relative frequency histogram. And for qualitative data, we studied two charts, bar chart and pie chart. Right, in this chapter, chapter number 2, we will start studying numerical measures. A numerical measure is a technique to describe data verbally. Suppose if you are talking about your data to someone on a phone call, how would you describe it? Describe him or her the graph? Of course, you cannot. So you have to describe something, some important aspects of your data, and those aspects would certainly be numerical aspects like average of your data or spread in your data, etc. We'll study those in detail in this chapter. And the second thing, and the second use of numerical measures is when you have to compare charts, you have to come with numbers. If the two charts are equal, if they are 50% the same, maybe they are 70% the same, or the mean of the two charts or the average of the two charts is different by 2 or 3 or something like this. So make you have to rely on numerical data or numerical measures if you are comparing charts or graphs. So these are the two main uses of using numerical measures on your data, and we will study more about these numerical measures in this chapter. Right, numerical measures can be divided into two parts. They are either for population or for sample. In one of our earlier lectures, we have studied about the population and the sample. Sample is a small subset of population. Sample is a small subset of population which is usually measured or measurable. Making every measurement or measuring everything in the population isn't possible, or it is very difficult. We studied that earlier. It is very difficult to measure everything in the population. Therefore, we have to rely on sample, and the statistics or the numerical measures that we compute on samples, they are used to estimate the parameters of population. Numerical measures calculated on samples, we call them statistics. Statistics mean something that changes. Since with the change of the sample, we have another sample, the numerical measure would be changed. Therefore, it is called statistic. Statistic means something that is going to change. For population, we don't use the word statistic. Numerical measures of the population, they are represented with parameters. Parameter is something constant, right? So if we measure, every measurement in population will come with a constant number, and that would be the parameter. But measuring that parameter is difficult because the data is very large. Therefore, we have to rely on sample, and the measurement that we make on sample is statistic. So based on the statistics, we estimate parameters, which is the basis of inferential statistics. Right, in this lecture, we will talk about the first numerical measure, that is, what's that? Measure of center. Measure of center. center. The first thing that we will study under measure of center is the arithmetic mean. Arithmetic mean. Arithmetic mean is also called arithmetic average or just mean, or it is called just mean. It can be calculated over sample as well as over population, but you should keep in mind that computing mean or average or any measure or any numerical measure on the data of population is very difficult and requires a lot of effort and time. So if we compute this mean on sample, of course that would be a statistic, and if we compute it over population, that would be a parameter. If we compute it over sample for some variable x, mean of variable, let's name this variable. We know that we give name to every variable. Let's give the name x to the variable. We call it x prime, x bar. This is mu. So the parameter arithmetic mean for population is mu. For sample, this is x loaded, x bar. How to compute sample mean? Of course, computing population mean would require going through every sample in the population and making a lot of measurement, which is really difficult, or sometimes it is impossible. So we have to rely on sample mean. We have to rely on sample mean. So sample mean is x loaded summation over all sample or over all measurements in the sample over n. What is this n? The sample contains some measurements, so n is the number of measurements. Measurements in the sample. We are going to study an example just after 1 or 2 minutes, and that n would be clear. And what is summation? This sum is a Greek letter. It refers to computing sum over all measurements present in your sample. Right, so this is going to sum n numbers. This means sum n xi's, x1, x2, x3, xn. So this summation operator, this is an operator. This means sum values of x with subscript I, where I ranges from 1 to n. x1 plus x2 plus x3 plus up to xn. So this is the formula to compute sample mean on a given sample having n observations or n measurements. Right, everything is set, and now we are going to solve an example. An example over some data. And the data given is x. The data x is given to be 2, 9, 11, 5, and 6. What should be the n? I've asked in my notes what should be the n. N is the total number of measurements in your sample. Let's count them. 1, 2, 3, 4, 5. So 5 is the number of measurements or observations in this sample. So we are given this sample X containing 5 measurements or observations. So the first thing is that we are asked to draw a dot plot for this. To draw a dot plot for this. Dot plot is this. We have already studied drawing dot plot where in chapter number 1. 2, 4, 6, 8, 10, 12. So the data is 2. So we put a dot on 2, then 9, put a dot on 9, 5, put a dot here, oh, 9, 11, 9, and then 11, put a dot here, and then 5, and then 6. So this is the dot plot. But this dot plot doesn't tell us about the central tendency or about the average or mean of the data. It gives us a good idea about the distribution of data. This is what we studied in chapter number 1. So it gives a good idea about the distribution of data, but it doesn't give you an idea about the average of the numbers. To do that, we'll apply the formula that we have just used, we have just learned for arithmetic mean. So let's compute sample mean for this sample containing 5 numbers. So this is very simple. X mean is summation from 1 to 5, because n is 5 now, xi over 5. This is excluded or x bar sample mean. So what we have to do is we can expand this by writing this x1 plus x2 plus x3 plus x4 plus x5 divided by 5, and then put these values. What is x1? X1 is your first number. X1, x2, 3, 4, and 5. So 2 plus 9 plus 11 plus 5 plus 6 over 5. So it gives us a sample mean equal to 6.6. But what is this x mean is? What is this x mean? X mean is sample mean, and of course the numerical measure computed on sample is statistic. We have just studied. It is a statistic. The numerical measure computed on sample is a statistic. But what's about the population from which we derived this data, or we took this data? What is the parameter of the population from which we have taken this data? Oh, that is difficult. How would you find mu of the large amount of data for which this is a small sample or a subset? Well, we don't have any better idea to guess the mean of the population than this. This is perhaps the best guess available on the data we have. So good estimate for mu would be the sample mean, and the sample mean is computed to estimate the parameter or the mean of the population, because applying this formula on all samples or all observations in the population is impossible, or it is very difficult. Right, before we conclude today's lecture, we have one more example. We have to solve one more example, and that example is taken from the last chapter, chapter number 1. In chapter number 1, we came across a data set and we called that birth weight data. Birth weight data, and we studied that data. It contains 30 samples of the birth weight of the weights of newly born babies. We studied this in chapter number 1. So birth weight data, and we experimented it previously, and we plotted a dot plot and a relative frequency histogram in chapter number 1 for this data. So in this example, we are going to solve the arithmetic mean on this sample, considering that the birth weight data of 70 kids given in this example is a sample. It's not a population. The population is the birth weight of all the babies in the world, for example. So that would be impossible to collect, or it is very difficult to collect. So we have to work with the sample of 30 babies that we have. So how to find the arithmetic mean on that? That's simple. We'll apply the formula I from 1 to 30 xi over 30. So this is the average or mean that we have been computing. This is the same formula that we use to compute mean or average in elementary classes too. So we can expand it, plus x1 plus x2 plus x3 plus x30 divided by 30. So you have to go to chapter number 1, read that data out. The first data sample, or the first measurement is 7.2. The second is 7.8, and the last is 7.7. So we have 30 measurements divided by 30 gives us 7.57. So you can experiment it at home and can compute the arithmetic mean of the birth weight data we studied in chapter number 1. Right, that's all for this lecture, and in our next lecture we will study two more measures measures of center, namely median and mode. Right, thank you.